All right. Hello again, guys, and hello to everyone who is watching in the recording. So today we are going to have you can consider it a recap. You can think of it as a recap. But I think more appropriately, it is sort of a deeper kind of like view into algebraic topics, which we use specifically in robotics. What do I mean by that? In linear algebra, you studied already something related to null space, something related to SVD, most likely. And you definitely studied something related to least squares, like solutions of system of equations, this kind of stuff. All of this is quite what we are going to, see now. But like right now, we're going to have a little bit of a focus. So it will be a little bit different from how it was presented before. More importantly, everyone, same as you, had this material. So it's like you're not the first who had this material. This is all of this is standard part of linear algebra. But it just happens that in robotics, what we are going to study in this lecture is extremely important. And somehow, even though everyone has it in their courses, like in algebra, etc., maybe if people forget, maybe something else happens. But you can clearly see the need for this for those topics to be covered. And in fact, you can kind of see clear advantages, for people who understand this topic. For the past 40 years, you can name people whose careers have been built on understanding fundamental subspaces in linear algebra. And I'm talking about robotics people. You see quite famous people who made big contributions, and the contributions can be traced directly to very good understanding of linear algebra. So while the materials that I'm going to give you is somehow just a recap of what you already learned, you can call it this way. In another way, I would personally say this is a key to getting a good career in robotics. Like what we're going to study today, like other things like Jacobians, etc., you're going to pick them up anyway. Without my lecture, you would pick it up. I'm pretty sure. But with this topic, fundamental subspaces, in my experience, it is often overlooked. And it is extremely important for our subsequent lectures, like for inverse kinematics, for task prioritization. Even when we are going to talk about dynamics, we're going to use the language of this topic. So, like my personal view, this is one of the keystones. So we absolutely need to, pay full attention to this. Also, it is kind of like 3 lectures in one. So in next 75 minutes, we'll cover enormous amount of material. So please pay attention the whole time. All right, introduction is over, motivation is over. Now let's get to it. First, let us start with simple stuff. Consider the following problem. You have to find least 2 norm, or the smallest 2 norm. 2 norm is Euclidean norm, you remember? X is the smallest 2 norm, for which ax equal to y has the least residual. This is called least squares problem. Okay, least squares problem. Let's try to understand what's going on. So residual is the difference between ax and y. So you have ax that should be equal to y, but maybe it isn't, right? You get some x plugin, you get something else, not y here. Well, the difference between ax and y is called residual error. Okay. So what we want is we want to find smallest possible residual. At the same time, we want to find the smallest x that provides this residual. So the theory somehow is that there are many x's which provide the same smallest residual. And among all of those same x's, you want to find the smallest one. That is the theory. Okay. This somehow implies that we will compromise. Kind of like we'll get the smallest residual, but that wouldn't mean we get smallest x or something like this. No, there is no compromise. The power of this, of algebra and this problem formulation, is that there is some x which provides smallest possible residual, and that it is not just one x. Usually, it is many such x's, and indeed, among them, you can safely choose the smallest one without compromising residual. So that is the important part. All right, good. Let us see how it's done. So solution to least squares problem, and least squares is what we call it, right? Is found this way. You realize that we want to minimize the residual, norm of the residual. To minimize the norm of the residual, you can save, norm of the residual, so ax minus y norm, second norm, remember. To minimize the norm, you can minimize the square of the norm. So the norm itself and its square have this their minimum coincides. So the minimum of this function is the same as the minimum of this function. They coincide. They exist. The same x minimizes both functions. All right. Now, how do we minimize this norm? How do we minimize, this quadratic function? Well, you take a you take a derivative, partial derivative, with respect to x, or partial derivative with respect to x. You get you get this expression 1. Then you open the brackets. You get a to go from here to here and here, and you get next expression, right? Then you notice that this guy hopefully is invertible. Hopefully is invertible. And if it is invertible, then you can write this equation here. And what you get is called pseudo-inverse. Like this guy here, we refer to it as pseudo-inverse. And we denote it with a sub plus. A upper script plus, right? That is pseudo-inverse. And that right there, we got two entities that we need to remember. First, solution to least squares problem. Second, definition of a pseudo-inverse. They're linked, they're one and the same. And we got two things. We understand now how to find least x, which provides least residual. And we understand now how pseudo-inverse is defined. Do we have questions? I'm going a little fast for this lecture, but I assume a lot of this material is already been covered. So I don't want to spend too much time on stuff that is probably a recap. All right. Notice there is one thing, I just mentioned one thing here. This guy will only be invertible when it is when A is a, what do you call it? What do you call it? Like a long matrix, right? Long matrix, wide matrix. And when A transpose will be a tall matrix, so wide and tall, right? No, wait, sorry, I'm making, what I'm saying makes no sense. When A is a tall matrix, of course, when A is a tall matrix, then this would be a wide matrix, and the product will be hopefully have independent, full rank. Or better said, if A has linearly independent columns, which is the key here, then A transpose would, of course, have linearly independent rows, and their product would be full rank. Then you can do this inversion. Caveat here is that I'm not sure if this is really required for pseudo inverse. I think maybe you don't have to have independent columns for pseudo inverse. In fact, I'm pretty sure you don't. So this definition of a pseudo inverse is more academic than practical. Just keep it in mind. And we don't really compute pseudo inverse this way. Pseudo inverse is computed completely differently, and I will show you how it is computed closer to the end of the lecture. All right, so I showed you where it came from, but that is not how it's computed, and we have like questions regarding this definition. That is just important to keep in mind, but the value of what you saw here doesn't diminish. All right, if no questions, then let's continue. We have a least residual solution to this guy, thus written as x equal to a pseudo inverse y. X equals to a pseudo inverse y. Good. So this provides us the smallest norm solution, which provides least residual. If A is full rank, it would give us zero residual solution, and it's actually going to be unique. When do we have many solutions? Well, when we don't have a full rank, right? So in case when A is full rank, we only have one solution. And not surprisingly, in this case, A pseudo inverse coincides with A inverse. So A inverse and A pseudo inverse are exactly the same when A is full rank. Good. Good. Now, let's consider this situation. We have equation ax equal to y. We want to find x that gets value of y as close as possible to y star. I don't know if this made sense, so let me repeat it one more time. So we want to find such x that provides us y star. So you can say y star is equal to ax, right? There is no guarantee that there exists an x which actually gets you y star, right? Maybe it is impossible. Maybe it is impossible. What is possible for sure is to get some y, but not necessarily y star, right? Sounds good. Sounds good. So the question is, can we find such an x that gets us a y which is as close as possible to y star? Good. Well, we know that for sure this would give us a least residual solution. So x equals to a pseudo inverse y star would give us least residual solution, meaning it would give us such x which minimizes the residual between ax and y star, which is exactly what we asked for. This is exactly what we asked for. Okay, so far, kind of the same stuff. But now, let us find the y that we wanted that we managed to achieve. What kind of y did we achieve? Well, if we multiply both sides by a, what we get is AX equals to A pseudo inverse Y star. AX in turn is Y. So what we get is Y is equal to A pseudo inverse Y star. Okay. So while this is a solution to the problem in terms of X, this is a solution to the problem in terms of Y. This X is the X that provides you a least residual to the problem. This Y is a Y that is possible to achieve, the best Y you can achieve. You cannot do any better. That is the best Y you can achieve. Okay, good. Notice, please, this interesting and strange construction that we observe here. You have a pseudo inverse, okay, and somehow it takes just any Y and gives you the Y that you can achieve. It acts as a projector. We'll see it in a bit in this lecture. I just want you to see how we got this construction here. Okay, good. So in a sense, you can say it projects Y star, sorry, into Y, where Y star was just any Y, just anything. And Y is exactly what you can achieve. Okay. Any questions so far? All right. Now we saw those preliminaries. Those were just material from, I think, algebra or analysis. Now let us consider the core concepts of this lecture today. Core concepts are 4 fundamental subspaces. 4 fundamental subspaces. What are they? Well, they are subspaces that any matrix has. So any matrix, you can say, has those 4 subspaces. They have names: null space, row space, column space, left null space. 4 subspaces. So our goal is trying to understand what they are. And we'll see what they're used for. Is intimately related to what we just saw before. We'll draw on this knowledge, so don't worry, we are not jumping into a wild new direction. Okay. Consider the following task. Find all solutions to the system of equations AX equals to 0. AX equals to 0. Let us try to find all of its solutions. Well, the same can be said in a slightly different way. You can say, let us find all elements of the null space of A. Okay. Let us find all elements of the null space of A. So null space of A is a set of all vectors, all vectors X that A maps to 0. Okay. So all vectors for which it is true that AX is equal to 0, all such vectors, for them, they cause null, they form a null space of the A. Okay. All right. So what we see here is just a task to find the null space of A. And it consists, as I said, just as one last time, of elements for which AX is equal to 0. We denote null space as N of A sometimes. You see this often enough. You can also denote it as kernel of A or null of A. Kernel is more for mathematical papers. Null is more for robotics papers or engineering papers. So it pays to know all 3. So fancy N, kernel, and null refer to null space. Okay. Now, in order to find all solutions to the system of equations, we can, because there can be infinite number of solutions, right? So it doesn't make a lot of sense to try to just speak of how should I put it, like a set of solutions. Like you wouldn't want to just list them. Here's one, here's another, here's another. Instead, you can find a basis in the null space of solutions, in the null space of A, right? So finding all solutions is the same as finding a basis in the null space. Well, this basis will contain all will describe all vectors belonging to the linear space. It is a quite typical idea of linear algebra. If you want to describe all vectors in a linear space, you just describe a single basis in this space. In our case, we'll even use orthonormal basis. Okay. In MATLAB, you can do it using the function null. N equals to null of A gives you a null space of A. In Python, using SciPy, there is this function called null space. So you can say SumPy linalg dot null space, and you get the same thing. So far, is clear?
Yeah.
Okay. So we have a space of solutions for AX equals to 0. And it is found using the simple operations, which can be called in MATLAB or Python. Of course, you can do it by hand too. There are plenty of methods. In school, you studied those methods. In university, you probably studied those methods. You can now come up with your own methods. It's it's algebra. It's relatively simple. But in terms of usefulness, maybe one of the most useful is to use optimized computer libraries, such as the ones that stand behind those functions. Okay, null and in MATLAB and in Python would be very optimized. Okay, good. Now, what is also interesting is that all solutions to this problem can be represented as x star equals to nz. So you can use this n as a basis. Therefore, you can use coordinates in this basis. And those coordinates would be z. And you can find any x that you want by multiplying basis by coordinates. So for any z, you would get a unique solution. Since this is an orthonormal basis, no two different z will give you the same solution. That is quite important, I think. So if you want unique solutions, you can just generate unique z, and you'll get unique vectors in the null space as a result. All right. Now, so this is just as I said. So if n is orthonormal basis in the null space of A, then if vector x lies in this null space, you can represent it as x equals to nz. Okay. So what I just said, right? X equals to nz. That also implies that you can have it can find coordinates for any x in this subspace, right? How do you find coordinates? As we studied in the lecture on basis, right? You say z, so coordinates of a particular x, if x is in the null space, can be found as z equals to n transposed times x. That's it. But that is only that is for x in null space, right? Of course, if X is not in the null space, if X is just a general vector, you can still do this. You can still do this. What would it mean? Well, you would find coordinates of the component of X that lies in the null space if you perform this operation on arbitrary vector rather than on the vector in the null space. You would find coordinates of the projection of this vector onto the null space. We'll get to it in a bit. All right. So as I put it here, vectors that are not lying in the null space of A, for them, you would get coordinates of the closest vector to them in the null space. And yeah. However, there are vectors for which the closest vector to them in the null space is a zero vector. That also happens. There are vectors which are such that the closest vector to them in the null space is a zero vector. We'll get to this as well. All right, let's just consider a few examples very quickly here. So consider this matrix 0, 1, 0, 0. Its null space is n equals to 1 and 0. Okay, how do I know? Well, I know that if you multiply this vector by this matrix, you get zeros. And I know that the rank of this base matrix is 1. How do I know that its rank is 1? Well, because I can give various reasons, which but you would have to ask me what do they have to do with rank, and we'll answer what rank is in a bit. But my reasons why I think the rank is 1 is it cannot be 2 because one of the columns is zeros, but it cannot be 0 because one of the columns is not zeros. And if the matrix has 0 rank, it essentially means it's any vectors that you input to multiply by this matrix will give you 0 output. So I know that the rank is 1. That's how. So it one 0 columns, another column is not zeros. Okay, good. Now this vector is also in the null space because it can be represented as a 2 times null space basis. This vector is also in the null space because it can be represented as 10 times vector null space basis. For this vector x 1 1, the closest vector in the null space is 1 0. And you can just trust me, say like, okay, yeah, makes sense. This element has to be 1 because it shouldn't change to find the closest element, right? But this element has to be 0 for it to be in the null space because no matter what you multiply here by 1, you would get not a 0 unless this is a 0. So you have to have 0 here. You can reason this way, or you can reason another way. You can say, okay, let us find 1 1 times n transposed, and what you find is 1. And then you can say, let's find this 1 is a coordinate, so coordinate of the closest element to x in the null space, right? And then you can say, let's multiply this 1 by n, and you get this answer. Here you can reason the same way. Here is another vector. Vector 0, 2. For this vector is 0, 2. The closest element to it in the null space is 0, 0. And indeed, you can, if you want, you can try to find like any other vector that lies in the null space that will be closer to y. Just try, see if you can manage. But I claim that it is 0, 0. And the way I can compute it is I can say, okay, let's compute coordinates of y in the null space. So it will be n transposed y would be 0. And then 0 times n gives me 0, 0. That is the process. Right. But after the lecture, if this somehow gives you questions, just try it. Just try to find closer elements in the null space than those two that I provided, and that would hopefully illustrate. Questions? Right. So far, it is a recap, and I know that bachelor students from our program usually have very good knowledge of this topic, so usually we don't have any problems. All right. Now, let us go a little bit forward and define things about orthogonality. So, for any two vectors, x and y, whose dot product is zero, it is said that they are orthogonal to each other. Okay. So two vectors, x and y, whose dot product is zero, are orthogonal. That is the definition of what orthogonal means. Okay. Next, vector x, whose dot product with any vector y that lies in the linear subspace y, is said to be orthogonal to the subspace. Okay, so a vector which is orthogonal to any y in the subspace L is orthogonal to this whole subspace. That's how we call it. Okay. Now, equivalent definition, the same but said in different words, is this. If for vector x, the closest vector from a linear subspace L to it is a zero vector, okay? So the closest to x vector from a linear subspace L is a zero vector, then x is called orthogonal to the subspace L. So those two definitions are equivalent, of course. Just take which one makes more sense to you. Okay, the one with the dot product, I think, is a little bit more elegant, but it uses this additional entity of a dot product, which is like it has a baggage of abstraction. Whereas here, closest, I think, as long as you are happy with Euclidean sense of closeness, I think is perfectly reasonable. All right, so for geometric intuition, you can use this one. But algebraically, maybe it is more useful to go with this one. Okay, questions? All right. Now, a little bit more definitions. So the space of all vectors y, which are orthogonal to a linear subspace L, is called orthogonal complement of L. And we denote it this way. So L perp. This symbol here is called perp. But I usually say L orthogonal. L orthogonal. So again, all vectors y orthogonal to a linear subspace L are called orthogonal complement of L. Good. Equivalent definition, the same but in different words. Space of all vectors y such that dot product of y and x is equal to 0 for all x in some subspace L is called orthogonal complement of L. As you can see, it is very, very similar. Yep, it's very similar. So if x is in L and y is in L orthogonal, This implies that dot product of those two vectors would have to be 0. That is important part for us here. So if x is in L and y is in L perp, L orthogonal, then the dot product is equal to 0. Okay? Questions? No questions. Okay, good. Now, let L be a orthonormal basis in the linear subspace L. So L, big L, is a orthonormal basis in the linear subspace. So take a vector x plus y, where x lies in L and y lies in L pseudo-inverse, oh sorry, L orthogonal. So you get vector A equals to x plus y. X is in L, y is in L orthogonal. So we call x a projection of A onto L. Okay. And we call y a projection of A onto L orthogonal. So again, we call x a projection of A onto subspace L, and we call y a projection of A onto subspace L orthogonal. Does it make sense?
Yeah.
So those are what we call projections. All right. So projection is the closest element in the subspace to a given vector. If we want to find projection of A onto L, we can do it this way. We can say x is equal to L times L pseudo-inverse times A. Please notice, we already saw it before. We saw it when we were trying to find the closest y to some y star that can be achieved as y equals to ax. So we were trying to find the projection onto a certain subspace. That's what we were trying to do. And in that case, it happened to be what we call column space. We'll talk about it later, range, etc. But you can see here, x is a projection of A onto the linear subspace L. And it is found exactly the same way as we were reasoning back when we were doing least squares. So since L is orthonormal, we can write it this way. X equals to L transposed A. Okay. Well, the projections. Those are projections. Any questions? Okay. Now, since A is equal to x plus y, and we know that x can be found as L transposed A, we can write, let me show it this way. We can put, instead of x here, the expression that we got here, right? And that's what we get. So we can easily just substitute here x, and we get this expression that allows us to compute y if we know A. And what would y be? Well, we shift this to the left, and we get this expression. We get y equals to I minus L transposed A. And that is where y is a identity matrix. And this gets us a projector onto the orthogonal complement of L. Okay. This gets us a projector onto the orthogonal complement of L. So what we see here is that if we want a projector onto L orthogonal, we just do it this way. Just look at this structure, I minus L, L transposed, and just kind of like notice it. I promise you, this is extremely useful. Like you can find a paper that describes something related to, let's say, legged robots. And in this paper, you would just have this, like, somewhere, just this piece of mathematics. It would just say, okay, this we compute as I minus matrix transposed, or matrix pseudo inverse. And looking at this, you instantly have to see this is a projector. This is a projector. So something is being projected here. And seeing it, you would be able to understand what the people are trying to do. You can tell me here, I'll give a pause to just give a little bit more motivation, but we'll get back to mathematics in just a second. You can pause here and tell me, I'm trying to be an engineer. I don't care about reading papers. So somehow this motivation doesn't work for me. Well, let me tell you, engineers that I work with, that I kind of personally interact with, do read papers. I think we are now at the point where engineers read scientific papers to do the engineering. It just depends, right? I'm talking about engineers who develop new tech, so stuff that hasn't been done before, and they have to rely on something. And what they rely on is papers from best teams outside. And those papers tend not to have explanations. For example, you would find this projector. No one will say this is a projector. They'll just put it there, and you should be able to guess what it is. And projectors have properties. We'll study it in a second. But if you understand that it is a projector, you can look up its properties, or you can remember them. Gives you a huge advantage in trying to understand the paper. So it's just one of many small things to note here. All right, do we have questions? Okay, let me move on. So let N be a null space of A. Then orthogonal subspace N orthogonal is called row space of A. Okay, row space. So row space is defined as orthogonal complement to the null space. We can have a different definition, much more difficult to digest, and that is row space of A is a space of all smallest norm solutions of equation AX equals to Y for all Y's. Okay. So you can think of row space as a space of smallest norm solutions. Or what is, I think, a little bit simpler, you can think about it as an orthogonal complement to null space. We'll denote row space as R, cursive R. We call it, I think, calligraphic. Like those letters, I think, are called calligraphic. I'm not sure. But and by the way, if you need to look up how I do any of those symbols, The source code for those presentations is in GitHub. So feel free to use any part of it. If you want to understand how those blocks are done, how like any of this is done, just take it. Sometimes it is nice to use full power of mathematical expression. So feel free to take from my lectures. Okay. Next. Oh, given vector x, so here is just 1 second. I think all my all my annotation kind of gear in Zoom covers titles of the slides. So given vector x, my matrix A and null space of this matrix denoted as n, and here we have like n means orthonormal basis in the null space, not just null space. When I use a matrix, I use it like normal, straight letters, as opposed to calligraphic ones to denote the linear subspace. Right. So we have vector A and its null space n. We can check if x lies in the null space. The simplest way to check is to just check this. Ax equals to 0. If Ax equals to 0, it lies in the null space by definition. And that is the simplest check. Sometimes, though, we don't want to compute Ax. For example, if A has a lot of numbers, a lot of elements, and N has a very few elements. That is not usually what happens in robotics, but you can imagine if A is a million by million matrix, and N is a million by 2 matrix, it is much simpler to operate with N than it is to operate with A. Less computations. So sometimes it makes sense. So how do we check? Well, in order to check that the element belongs to a subspace, you need to check that it has 0 projection onto the opposite subspace. Okay? 0 projection to the opposite subspace. So this would be a projection onto the null space. So this together would be a projection onto the orthogonal complement of the null space. So in other words, this would be a projection onto the row space. I minus n transposed gives you a projector onto the row space. And if it is 0, it means the vector completely lies in the null space. By the same logic, if you want to check that the vector lies in the row space completely, it has to have a 0 projection onto the null space. So n transposed have to be equal to 0. Okay? By the same logic. All right. Good. Any questions here? All right, let's continue. Now, let me give you like another task. Find all vectors y such that y equals to ax. Find all possible y's that can be achieved this way. This is called column space of A. This is column space of A. Column space of A is a set of all outputs of the matrix A for all possible inputs. We'll denote it as C of A. In the literature, it is sometimes called image of A. Image, same as kernel, are terms more used in mathematics. In engineering, we more often use null space and column space. Okay. Now, how do you find an orthonormal basis in the column space? Well, this is a much older topic than finding bases in the null space. Finding orthonormal bases in the column space is called orthonormalization of a matrix. And I think in your algebra, you probably studied Gram-Schmidt procedure. Gram-Schmidt procedure. That is a procedure to find find orthonormal bases in the column space of matrix. I'm not sure if you called it this way, but we usually call it orthonormalization of a matrix. But it is just a find orthonormal basis in the column space. So in MATLAB, you do it this way: orth of A. In Python, it is Python of SciPy, and you do it orth of A. That's it. It's very simple, right? So if you want to find all unique outputs of A, you can find them as all such S sub Z times Z for all Z. If S is your orthonormal basis, you could have used this one. You could say, if I want to generate output of A, I can just multiply it by X. Well, this might contain repeated entries. If you use the same, if you use 2x from the same that have the same row space projection, it will give you the same output. So somehow using this would give you better results than using this if you don't want repeated entries. Okay, that is not very important. It's like just a little bit of algebraic information. Now let's get to a little bit of application of those. So let A be a square matrix. So A maps input X in Rn to output Y in Rn. Okay. So if it has a non-trivial null space, non-trivial in mathematics means null space that contains other things other than zero vector. Trivial means it only contains zero vector. For subspaces, that is how it works. If you have, you cannot have a linear space that does not have a zero vector. The worst you can have is a linear subspace that consists only of a zero vector. But zero vector always, like any subspace you can come up with, would have zero vector in it. So it is called linear trivial. We cannot say empty subspace because there is no such thing as empty subspace. For even full rank matrix would have trivial null space consisting of a single vector, 0. So that when I say non-trivial, I mean subspace which has dimensionality other than 0. Okay, so if it has non-trivial null space, it follows that multiple inputs can be mapped to the same output, what I said before. So let's look into that. So consider you have this expression, y equals to a times r times xr, where xr is in the row space. Well, it is the same as a times xr plus xn, where xn is in the null space. Okay, so you can get any xn in the null space, generate hundreds, millions, how many, just as many as you want, and you would get different vectors here. The sum would change for any new xn, but the output will stay the same. So many vectors are mapped to the same output y. So in fact, if null space has k dimensions, it implies that k-dimensional subspace of X is mapped to a single element of Y. So the dimensionality of the column space would be n minus k in this case. Okay. So given a vector y and the matrix A, let's find the projector of y onto the column space. As you can kind of guess, we can project anywhere. So column space included. How do we project onto the column space? Well, if we knew column space orthonormal basis in the column space, so if we knew C as orth A, then what we could have done would have been, say, y star is equal to C transpose y as before, right? But if we don't have C, what we can do is do it this way. We just find the projection by multiplying by a pseudo inverse y. So we multiply y by a pseudo inverse. Notice it is the third time we see this, and now we finally understand what's going on. So this thing here is a projector onto the column space. If we have linear subspace given by a basis, like in the example with L, you remember we had the subspace L given by its basis L. So if we want to project onto L, we just multiply by L pseudo inverse. If the basis is orthonormal, L transposed. And when we were doing in the very beginning of the lecture, those acrobatics with least squares, what we were doing when we were saying, let's find the y that is the closest y to the current one that we can achieve. We were projecting y onto the column space. And here we done exactly the same. So that's what we were doing. We were inventing projectors. Okay. So you can say this feels nice. It doesn't require computing orthonormal basis. So previously we relied very heavily on computing orthonormal basis, like using null or orth. Here we don't have to. We just use pseudo inverse. However, both null, orth, pseudo inverse, even a rank, all of those operations require the same exact procedure. Procedure is called SVD decomposition. So all of those operations that we studied today require SVD decomposition. So in terms of computations, they're equivalent, all of them. All right, good. Questions so far? Okay. So similarly, you can define projectors on the row space. Given element X and the matrix A, we can find projector of X onto the row space of A as X row equals to A pseudo inverse AX. So this is the projector. Why is it like this? Well, like memorizing it is very simple, but you can get like an idea. How you can think about it? Well, you can say first we compute output that X produces. So this, what I boxed, is somehow like a Y produced by X. Okay, the output produced by X. And then here we try to find what kind of a smallest norm input could have caused this output. You understand? So first we produce output, and then we guess what is the smallest norm input that could have caused this output. And this instantly means we will get the smallest norm X, which produces the same Y as X produced. So XR will be the smallest norm vector that produces the same output as X. And what would be the difference between XR and X? Well, it would have to lie in the null space of in the null space of A. Why? Because the difference does not produce any change in the output, and the vector that produces no change in when I say produce no change in the output, I mean if you multiply the difference by A, you'll get 0. So, and any vector whose output is 0 is in the null space. So the difference between those two vectors in the null space, that means that they themselves, so that means that XR would have to lie in the row space, right? Okay, okay. And it will be projected onto the row space of X. Okay, so row space component of X does not change under this operation. So this is how you can think about it, but you can just memorize it. So this is not difficult to memorize, I think. So you can, if you want. Now, just one fact. This guy projects, the output of this guy of pseudo-inverse lies in the row space. Same as output of A lies in the column space, output of A pseudo-inverse lies in the row space. We'll prove it later. Okay. Also, we can prove that the row space of A is equivalent to the column space of A transposed. There are plenty of stuff we can prove. Okay. If you have questions, just interrupt me. I'll go on. We have 9 slides to go. I hope we'll manage. Let's see. Last subspace. Subspace orthogonal to the column space is called left null space. So left null space is a space of all vectors y orthogonal to the columns of A. So you can say it is a space of y such that y transpose A is equal to 0. That is the definition. And it is useful. It is useful to think of left null space as a space of all things that you cannot achieve. Like you have AX, there are vectors Y that you cannot produce. And those vectors Y can be mixed with vectors that you can produce, of course, right? And they would, if there is a vector Y1 that you cannot produce and a vector Y2 that you can produce, the sum of Y1 and Y2 still cannot be produced, of course. But you can have this pure negativity, like just vectors that cannot be produced, and the closest ones to them that can be produced is 0. Those vectors form left null space. Okay, is orthogonal complement to column space. Okay. We can prove that left null space of A is equivalent to the null space of A transposed. So there is this equivalence, right? Row space to column space of the transpose, left null to the null of the transposed. Okay, good. And this equivalence is important even in practical sense. If you want to find row space orthonormal basis in MATLAB, there is no function. What you have to do is find orth of A transposed. Same for left null. There is no function in MATLAB or in Python. What you have is to find null of the A transposed. Okay. If you want to project a vector y onto the left null space of A, we can do it this way. We already saw this before. This was to check that there is a that the vector lies in the column space. We were checking that its projection onto the left null space is 0. Now we can see what was going on. This is a projector onto the left null space, right? And logically, you can kind of figure out how it works. If you open the brackets, what you would see is y sub L is equal to y minus projection of y onto the column space. So you subtract from y everything that had to do with the column space, and what you're left with is a null space. So makes sense. If C is orthonormal basis in the column space of A, then you can do it this way. Okay. Now, last block of this lecture. I understand that probably you are a little bit tired, but is extremely important. So let's just try to survive a little bit longer, or try to pay attention. So there is this thing called singular value decomposition. It is given like this. You have probably seen definitions which go something like U times sigma times V transposed. I prefer this way of describing it for the purpose of fundamental subspaces. So the decomposition goes like this. Any L can be represented as one matrix which consists of bases in the column space and left null space. Then a diagonal matrix of singular values. Here you have singular values, here you have zeros. Sigma is a diagonal matrix, and it is sorted from biggest to the smallest element. Here you have row space and null space, transpose, notice. So you have this decomposition. But since you have zeros here, all of those zeros are going to kill off the L and N after multiplication. So what you actually have is just this. You have column space times sigma times R transposed. And this is called economy SVD usually. So SVD which does not compute L and N. Okay. So C is column space, left null space, row space, null space. Okay. Next. Rank of the matrix is the size of sigma. That is a little bit backwards definition. The way we rank is computed in MATLAB, for example, is you find sigma. It's going to be vector of a lot of numbers. Then you do a cutoff. You say any number less than 1 over billion will be deleted, replaced with 0. And then you count how many non-zero elements there are. They are sorted, and that is your rank. But yeah, so rank of a matrix is computed as the size of sigma, as number of non-zero elements in the sigma. Now, pseudo-universe is defined this way. We just switch around C and L. Like this guy used to be on the right, this guy used to be on the left. They switched places, and we have inverse here. We can simplify it this way. We can simplify it to be A pseudo inverse equals to R sigma inverse C transposed. Sounds good? That is how a pseudo inverse is defined. Instead of C, we have R. Instead of R transpose, we have C. And here, very importantly, we have inverse. Notice this inverse may sound to you as like, why inverse? Isn't it a costly operation? No, it's not costly, because inverse of a diagonal matrix is just replacing diagonal elements with 1 over. So it will be 1 over sigma 1, 1 over sigma 2, 1 over sigma 3. So this is actually computationally cheap. And this proves that A pseudo-inverse lies in the row space of A. How? Well, notice that the output is R. So it has to lie in the row space. Whatever you multiply R by on the right, it will still provide you output in the row space. Okay. Now, let us find SVD decomposition of A transposed. Well, SVD decomposition of A transposed gives us some column space, left null space of the transpose matrix, R and N of the transpose matrix, sigma of the transpose matrix. Okay, now let us transpose this matrix to get A. So we want to get A. We have to transpose this whole thing. And notice the transpose of a diagonal matrix is still itself. So here's what we have. We have that A is equal to this guy after transposition. You can check me after the class. I'm going a little fast, but you know what I did is let me show you. I guess this guy went here. This guy went here. Right. That's it. Okay. So notice instead of column space, we have row space of the transposed. Instead of left null space, we have null space of the transposed, and vice versa here. So we see where the relation comes from. Column space is a row space of the transposed matrix, and null space is the left null of the transposed matrix, etc. So if you can find one, you can find the other with transposition of the original matrix. So that's how it works. Okay, and importantly, you can see how it is proven. Very simple. Now, last stretch. So we have this thing, column space projector, and as equivalent to this thing. Let's prove it. How do we prove it? Well, we get this guy. Its decomposition is here. And decomposition of the pseudo-inverse is here. Well, we know that this is identity because it is two orthonormal matrix times itself is identity. Definition of what orthonormal matrices are. This is again identity. So we get what we wanted to prove. One more. Let's prove that projector onto the row space is indeed R transposed. Well, again, we have here pseudo-inverse, here original matrix. We notice that this is identity, then this is identity, and we get to this expression here. Again, beautiful, nice. And we prove very strange things about those matrices. Last property of the projectors. So we denote a projector as P. Okay. Let us prove that P times P is equal to P. So that projector times projector is still the same projector. That is fundamental property of projectors. So we prove it this way. We say A transpose should be equal to A pseudo-inverse. Well, here's A pseudo-inverse, here's A pseudo-inverse. We notice that this is identity, this is identity, this is identity. Then we notice this identity, this identity. And that is how we prove that this is equal to this. And we previously proved that this is equal to this. So that is a proof. And in the same way, we can prove that a projector of this kind would also work. All right. I hope we saw enough to keep us, from, I don't know, treating algebra lightly. I hope I didn't scare you too much. What we saw today is, I think, extremely important, but also is the foundation for quite a bit of methods that are used in robotics. Projectors are everywhere, especially in kinematics, and even in dynamics. Next lecture, we'll use this material to solve inverse kinematics and analyze Jacobians. All right. Do you have any questions for what we saw today? If no, then we'll see each other in 2 days. Hopefully, if you can look up through the slides, see what concepts you didn't know before, and hopefully next time we see each other, we would apply those things. Right. See you then. Bye bye.
Thanks.
Bye.